All right, now that you have some idea of what's going on inside the instrument, I think, or at least I hope, it will make it easier to understand why the spectra look like they do and maybe how to interpret them. So we're going to be looking at carbon-13 NMR, and so most of the carbon atoms have 6 protons, 6 neutrons. They have an average atomic mass, or an atomic mass of 12. These carbons we're not going to see because they have an even number. But carbon-13s show up well in an NMR, and so those are the ones we're going to look at. So we'll talk as if we're talking about, or we're looking at carbons, but really we're only seeing that fraction of the molecules that have carbon-13 in them. It happens naturally and somewhat randomly distributed, so we get a good picture of the molecule. So I have 2 molecules on the board. Try to start with something kind of simple. You'll look at a little bit more complicated things in lab. 3 carbon, hydrocarbon, 3 carbons long, this chain is called propane. And down here, essentially the same molecule, but we have an OH, which in organic chemistry we call an alcohol. The OH is attached here at the 2 carbon, and this is propanol. So methanol is a 1 carbon chain with an alcohol group. This is propanol. In the middle, this is actually technically called isopropanol. This is the same thing as rubbing alcohol that you have in your medicine cabinets, perhaps. So we have propane and propanol, similar but a little bit different, and we'll see what their spectra look like. Well, on our x-axis, the units are a little bit confusing, and I'll explain those in a second. They're listed as part per million, which sounds like a concentration unit, which is very odd. Once we go through here, hopefully you'll understand what this means. But basically we have energy on this axis, and the question really is how much energy, so now we're talking about the RF frequency, how much energy, or how intense, how energetic of RF radiation, what is that frequency that causes this nucleus to flip its orientation? So there are 3 carbon nuclei, and they're all going to flip their orientation with a specific RF frequency. And the question, of course, is which one, which frequencies will cause that to happen? Well, if I'm predicting, of course, in lab you're going to be working through some of this where you're predicting what the spectra look like. At one point you're going to collect a spectrum, so you're really working the other direction. But if I'm looking at propane and trying to figure this out, basically on this axis, what we call 0, the carbons will resonate in the scale from about 0 to 200 part per million on this scale. It's somewhat artificial that we create. The 0, right down here at the end, this is going to be the most normal, most basic kind of carbon. So you can imagine something like methane showing up down here. Well, if this is normal, and the other things, as things become more interesting, for the most part they're going to show up what we say downfield, or shifted to the left on this axis. So the question is really why? Well, it has to do with the electron cloud that exists around these nuclei. So this carbon, think about the nucleus, that's really what we're talking about. The nucleus of this carbon is actually somewhat buried inside this molecule. So does this nuclei feel the full force of the magnet of the NMR? And the answer is really it doesn't. So it is nucleus, it's inside this powerful magnet, but between it and the magnet are the electrons of the carbon and the hydrogens around it, the other carbons, these other atoms that are attached to the molecule. They all have their electromagnetic fields, and they essentially work as a buffer. So this nucleus of this carbon has some other stuff sort of buffering the effects of the magnet. So what we basically just pick a molecule, something very simple, and we say, okay, well, we'll say this is normal resonant frequency for carbon, and we'll call that 0. Then, as the molecules become, like I said, more interesting, we're going to see things that you attach actually pull electron density away from that nucleus, away from around that nucleus. So as you have other things attached to it, and especially electronegative groups like an oxygen or a nitrogen or chlorine or fluorine, you get those electronegative groups attached, they pull electron density away, and so the buffer around this carbon nucleus gets smaller. And as it gets smaller, we say it's deshielded, as it becomes deshielded, it actually feels a greater effect of the exterior magnet. It feels more of the magnet. Now because of that, its excited state is actually bigger, a little higher in energy. So you can think of it this way: we have to put in more energy to get it to flip against the magnet, and when it flips back, which is what we observe in our experiment, it's going to give off more energy. So this actually turns out to be on the left of the scale. This is higher energy, and this is lower energy. So we'll start with the propane. When we look at the molecule, the first thing you want to do is figure out how many are basically the same. And there's symmetry here, so take advantage of it. This carbon on the end and this carbon on the end are basically the same. They're symmetrical, right? We could rotate this around and they'd occupy the same location. Terminal hydrogens, for the most part, are going to be the most upfield shifted of any of the carbon atoms we see. So if you have 4 or 5 peaks here, assume the first one, farthest right, is going to be a terminal or an end carbon. So at this point we'd say these two are pretty much the same, and they're on the end, so they're going to show up in this direction. And carbons that have more carbons attached to them, the more substituted or more branched they are, or if they have electronegative groups, that's going to cause them to be downfield shifted a little bit. So we've got this center carbon, which is going to be further to the left. Not too far downfield, but it's probably going to look something like this. So my spectra might have this appearance. So what does this make me think if I were to see this spectrum to begin with? Well, I've got some terminal carbons, and I've got some carbon that's in the middle, and the intensity tells me something about how many carbons. So this is twice as big as this carbon, so it's probably 2 terminal carbons attached to one in the middle. And it turns out that for this molecule or molecules like it, this type of carbon always shows up right here. It'll be somewhere around 10 parts per million or so, but it's always going to be there. So you can go to the charts, the types of things that you have in your lab handout you're going to be working with in lab, and you can actually start to assign some of these because of where they show up. Alright, but let's add something electronegative. I want you to see this a little bit more extreme. Any branches, double bonds, triple bonds, those things, same effect really as these electronegative groups, are going to cause these things to be really far downfield. Alright, first thing I'm going to do here with the propanol is once again look for how many carbons, how many unique carbons there are. And like before, I think this first one and the last one are pretty much the same. And they're going to be the furthest upfield or to the right. Now, this carbon here, compare this terminal carbon with the terminal carbon in propane, this one is actually going to be further deshielded, even though it's not directly attached to this oxygen. This oxygen is pulling electron density because it's very electronegative. So this group is going to be downfield a little bit more than what we saw in the first case. And then we have this middle carbon, which we knew was going to be downfield because it's internal, but because it has this alcohol group, it's going to be way down here. And so, once again, we get maybe a 2-to-1 ratio, which tells us something about the amount we have, and how far downfield tells us a little bit more about the identity of things. Now, in lab, you're going to see some longer molecules, some branch, some things a little more complicated, but I think hopefully with the tools you have, you'll be able to make sense of it. So, have fun.